ceremony. And we are, as the committee of the 4th ISPG Research Forum 2021, appreciate you to join with us today. And for a brief moment, ladies and gentlemen, we would like to invite you to rise and sing the Indonesian national anthem, Indonesia Raya. Thank you. And next, we will explain to you about our standard operational procedure of our webinar today. The first is your nickname must be the same as the registration form. And the second is make sure that your audio or microphone is on a mute mode to avoid interruption. And the third, please kindly to always open up your camera during this event. And that was only the beginning, ladies and gentlemen, because today we have a very special guest. Please welcome to Mr. Julianta Panjaitan as the President of Indonesian Society of Veteran Geologists to deliver the welcoming speech. To Mr. Julianta Panjaitan, time is yours.
Thank you, Bang Adit. Bang Adit is the pre-event and post-event chairman. So again, it's an honor for me to be here with all of you to have a post-event, the 4th ISPG Research Forum, again on behalf of ISPG as a sub-organization of IAGI, Indonesian Association of Geologists. We are happy to have you, Mr. Saikardas, to share your knowledge about formation, evaluation in deep water. As you know, this post-event basically following up our pre and main event, which already conducted last week, and hopefully by having this technical course from industry, which we get supported from Baker Hughes, all the participants and the committee will have a deep knowledge and technical knowledge about the technology, on this case about formation evaluation in deep water. Our government target in 2030, which is 1 million BOPD and 12 BCF per day, is put it as a high priority from the government side. And from organization point of view, these technical courses will help us to elevate and disseminate the formation evaluation technology and understanding. And hopefully by having this kind of seminar, all participants can have understanding and can ask the question if you have something in your mind, and if this is applicable also in your field. Again, on this Ramadan month in fasting period, I would like to say selamat menunaikan ibadah puasa to all of my Muslim friends, and hopefully we can still safe and still healthy in this pandemic COVID-19 situation. Thank you, committee, and enjoy the seminar from Mr. Saikardas. I give back to Mas Adit.
Thank you, Mr. Julian Tapanjaitan, for the welcoming speech. Ladies and gentlemen, our discussion today will be delivered in English, but don't hesitate if you would like to give your question in Bahasa Indonesia on the chat box by following the format name underscore affiliation and underscore question. So without any further ado, ladies and gentlemen, we would like to call Mr. Saikatdas. Good afternoon, Mr. Saikatdas.
Hi, good afternoon, everyone. Hopefully, you can hear me properly.
Yes, how are you, sir?
I am doing well.
Yes,
And
thank you. And I assume that our discussion today will be very interesting since the government of Indonesia through SKK Migas already set the target. There is one a million BOPD and 12 DSCFPD in 2030. And if we see the latest publication from SKK Migas, we can see that the deep water exploration is one of the strategy to set to achieve that goals. So we hope that our discussion today could be useful for all of us, the government, the practitioners, academicians, and also students. So without any further ado, we would like to give the screen to Mr. Saikatdas. The time is yours.
thank you. Thanks a lot. And thanks a lot, Pak Julianta, for those nice words. Yeah, I'm absolutely delighted today to be here. Thanks a lot for inviting me to such a prestigious conference. And I can see there's a lot of participant and I'm really honored to be here. So let me try to share my screen so that let's see whether it can be done properly. Okay, let me go to the presentation mode. Just give me a second. Share screen. Not sure. Can you see my screen?
Not yet, sir.
Okay, let me share it again.
Yes.
Okay.
You can see it now, I believe.
Yes.
Yes.
Perfect. And you can hear me properly as well.
Yes, we can hear you, sir.
Oh, okay, great. So yeah, then without further ado, let's definitely discuss about the technical presentation that you are inviting me to do. First of all, definitely thanks again for inviting me. I'm really honored and really glad that I get the opportunity to talk to you on this. So yes, understanding the challenges and the target of what you have described, I do certainly believe this can be a very pertinent topic to that aspect. Deep water is always a frontier that everyone is going to increase the reserve to produce more and more, just because most of the easy access reservoirs are pretty much explored. So when you need to go for further and more complicated reservoirs to go for to add more reserves or to produce more. So certainly that's one of the reason that deep water has become a point of interest in many of the countries, and I believe Indonesia is definitely one of them. So yeah, today we are going to talk mainly about formation evaluation. I am throughout my career, I'm a petrophysicist. I work with formation evaluation for last 16 years with Baker Hughes. And currently I am the discipline lead for Asia Pacific. So I have worked with many deep water formations and I'll be glad to share my knowledge with you today. So this is the objective and the outline to summarize what we are planning to discuss today. So first and foremost, understanding the different architectural element of deep water deposits. That I believe is the most important and the fundamental thing to start with. Then only we can understand the complexity of this formation evaluation in deep water. And once you accept the challenges, then only the solution will come. So after that, after understanding those elements and the complexities, then we will talk about some solutions that will involve 3D multi-component resistivity measurement, NMR measurements, to do a detailed petrophysical evaluation for those kind of deposits. After that, we will discuss more about image log for geological interpretation. The main challenge that what deep water formation evaluation poses is the link between the petrophysics and geology is very important in this kind of scenario because of the challenges, complexity of the depositional environment and the processes involved. That connection needs to be made. It cannot be done standalone. You cannot just look at density, neutron, and resistivity, do a formation evaluation, and you say, okay, my job is done. That is definitely not going to happen when you deal with deep water. We need to connect the formation evaluation with geology, and that makes things really exciting. And image log is something that does it for us. And then after understanding of the formation evaluation, we need to know about the fluids, because at the end of the day, fluid is something which defines a success of a project when it comes to petroleum. So yes, we will talk about the efficient way of identifying the fluid and sampling in the deep water setting. And then we will talk about integrating all these knowledges that we discussed and how it can help in an efficient evaluation of deep water deposits. Okay, so that is the outline. So let's start with something very basic, to understand the processes and components of deep water depositional environment. So let me take my pointer so that it will be easy. So if you look at this picture, the picture comprises two things. One is processes, which is at the left-hand side, and the deposit, which is at the right-hand side. It's a cartoon to make you understand what are the different processes involved in a deep water setting. Starting from the this is the land, and you can see it's going to shelf and then slope and then going to the deeper part of the basin. So this side we are discussing about the processes. First process, let's say, is the sediment gravity process, which is the very standard and natural and basic process to start with. That will involve slide and slump and debris flow and turbidity current. This is what we generally expect in a deep water setting. But it's not all. You can have canyons, you can have channels. That is causing more an additional input to those processes. You can have the bottom currents, which we generally call the contour currents. You can have the wind driven bottom currents. You can have a tidal bottom currents in the canyons, and then the pelagic and hemipelagic settings. So all these processes are affecting the deep water deposits, which makes it more and more and complex. So once we understand these different processes, let's see what are the deposits that we can get in deep water. Again, if you see that the standard deposits that we always come to our mind is like turbidites, the slide, the debris flow, the slump. Other than that, we can always get a channel when you have levee and lobe and that kind of complex. These channels can be one or multi-layer channels. Then you can also have the contourite, which is the output of the contour currents. Then you have the basin deposit that can get complex more with the pelagic and hemipelagic deposits when we are talking about organisms which is coming into play. So now you think all these things that is happening in a deep water environment, this is what you can expect in a deep water setting when you go for deep water formation evaluation and exploration. So this picture will let you appreciate the complexity of the process and the complexity of the deposits that we are going to encounter when we plan for deep water exploration. So understanding that fundamentally is extremely important for any petrophysicist and formation evaluation person to get a complete idea about the formation evaluation. You know? So So as we understand the complexity, let's go to the next slide. And I will, whenever we talk about deep water deposit, the first thing always comes in mind is a thin bed, laminated sand shell and a kind of setting, um, low resistivity kind of setting. So let's see what kind of setting that these kind of low resistivity pays or thin beds are associated with. In the previous slide when we were discussing about different deposits. So this kind of thin beds can be associated with a sheet kind of deposit. It can be associated with the channels. The channels can be of multiple types, composite channels, single or multi-story. Then actual thin beds, which is always there in this kind of setting, which is associated with many other things like a levee, slope, interchannel, interbedded with other things, which we are talking actually in the top part, which is the basin plane or inner outer fan or the mid fan. All those kind of areas you can have thin beds as well. And after that, we always have the mass transport complex, which is generally a non-reservoirs. So these are the different types of deposit that we always encounter when we drill a hole. The top three are generally considered reservoir, and the mass transport complex is definitely non-reservoir. We want to uh, avoid that. But you can understand that, yes, when we talk about deep water, these are the different types of reservoirs we deal with. These are the different types of reservoir poses different types of challenges. So long story short, it is definitely a complex kind of setting and we need to know more about it. To emphasize more on this in terms of in a cartoon, which is easy to understand where we have more potential and where we have not. So let's say you drill a well through those deep water deposit. You can always encounter some MTC, which is the mass transport complex. Generally, that is not our reservoir. That is a poor quality of reservoir. Then you can also encounter slump. Slump can be sometimes good. Sometimes it has got very good quality sand associated with it, but sometimes the extent of those kind of reservoirs may not be that great. So it can be both ways. That's why we have a kind of a neutral phase. And then the debris flow. Debris flow can be also a very good quality reservoir, good sorting, very nice sand reservoirs, good porosity. But again, it can be discontinuous, which can cause some other problem. So you can be lucky to get a good quality reservoir, good production from that, or can be sometime may not be that lucky. So again, a neutral one. But something which is a really good and well known and well understood, many people actually go for that, is the turbidite because it's extensive. It has got good quality sand. Generally, you always have a clean sand at the bottom. After that, if you go up, it will be more associated with silt and it will be associated with laminated sand shell sequence. So this turbidite deposit is generally a sought after reservoir when it comes to deep water deposits. So understanding of the dimension, not only just the porosity and permeability and the resistivity, but understanding the dimension, geometry, and the reservoir property is extremely important. We somehow need to bridge it together to do a proper formation evaluation when it comes to deep water. Giving another example, this is an actual example when we log, and I'll explain the tracks to start with. The first track is a gamma ray, so and the second track is density neutron, and the third track is resistivity. Standard normal data set, a standard quad combo data set or triple combo to be honest, to start with. So if you look at the gamma ray, that's what we generally look for to start with when my reservoir is. So the lower part of the reservoir, you see, you have a lower gamma ray. Generally, that means it's a sand section. Density neutron, which is on top of each other, that is another indicator of good quality sand. And you see an increase in resistivity, which is also an indicator of having hydrocarbon in that reservoir. Whereas the top part, you will see it's not a very good quality reservoir at all. It's the gamma ray is a bit higher and the density neutron there is separated. You have a resistivity which is not that high. So this, if you do a standard log interpretation, obviously we will come up with an interpretation that the lower portion has got more potential than the upper portion here without any other information. But when you have, and with that, if you go for a production kind of approach, like go for a DST and stuff, that what they did, I will come to the image log, which is here a little bit later, just to make it a little bit more clear, because most of the time we are left with only these three logs. And then if you go with that and do a tasting, that what here happened, and found out that this area is actually less productive than the top part. That is a surprising thing if you do not have any additional information. When we looked at the image log, when we do a formation evaluation and including the image log, we could see that the lower part has got a slump thin beds. That means it's not a very continuous. And you can see that I have put a picture of an exposure to show you what exactly that means. So you will see all the beds are kind of convoluted and slumped, so that it is not continuous. So it can be a very good quality sand. You encounter a very good quality sand. But when it comes to production, obviously because the sand is not continuous, the production is not that great. Whereas at the top part, this is a laminated thin beds. You can see what it actually means from a picture of this exposure. These kind of thin beds, it has got a lot of shale in it, no doubt, but the sand associated in that laminated sand shale sequence, they can be really very good quality, very porous, permeable, and when you produce, it can produce for nicely without any problem. And because this extent of this laminated thin beds can be really, really large, that can be a really productive zone which can keep on producing for a longer period of time. So that's the point, is like only looking at the standard logs may not be a very representative formation evaluation when it comes to this complex setting like deep water. Okay, so we need to have more data set, advanced logs, and more information to unveil this complexity, to understand it properly, and do a proper formation evaluation. Giving you a little bit more from the production side, this is a work that was done by Weimar and Pettingill in 2007. What they did, generally what we know, if the flow is high, if high flow rate equates with high well ultimate recovery, that's what a general notion is. And it is true in most of the cases. But when it comes to deep water, what they did, they gathered some data, the data about the well ultimate recovery, which they plotted in the x-axis, and then they plotted well flow, flow rate in the y-axis. And then you can see there is a huge amount of uncertainty. The distribution is quite large. So even if, let's say, if you take this point where the well flow rate is really high in the initial phase, it produced quite a lot, but the ultimate recovery is not that much. Whereas if you look at this kind of wells where the flow rate is not that much, but the ultimate recovery is very high. It kept on producing for a longer period of time. And we have seen this in many, many places. So again, coming back to the point, so just looking at standard formation evaluation, looking at a good porosity, permeability, and then get excited about it, may not provide the actual picture of that particular reservoir. Depositional elements have different productivity expectations, so that needs to be understood. The advanced data needs to be acquired and interpreted to make it a better formation evaluation. Hmm? So that was the stage that I wish to discuss. I wish to define the problem so that you understand why we need to have a more complex data set, more advanced data set, advanced solution when it comes to deep water formation evaluation. Why density neutron resistivity may not be the best idea to go for, you know? So this is a deep water formation evaluation workflow that many of the people uses. We also use a lot in many deep water setting in many part of the world. So we have this workflow which has got three lines, you mean to say, which is catering to three different problems that we discussed. One is the uncertainties, which is related to geology. Another one is the uncertainty which is related to the saturation. Another one is the uncertainty which is related to the porosity distribution. Yeah? So we need to tackle these three problems separately to start with, and somehow we need to integrate to come up with a ultimate formation evaluation. How to do it? As I said, geology is extremely important when it comes to deep water because the different reservoirs which may have very similar petrophysical properties can be associated with different type of depositional environment or depositional setting, which has got a really strong bearing on the formation evaluation of that reservoir or how the reservoir is going to um, produce in the longer run. So that uncertainty can be reduced by acquiring image log, interpreting the image log. So first, obviously, we start with the bedding and the depths. Then you can do a thin bed analysis, which is mainly to do with the petrophysics, but I will leave it aside for the time being. But main information from the geology aspect that what we can get from image log is the lithophase association, depositional environment association, and the settings that these reservoirs are actually situated in. As I said, that can be a very pivotal information to understand the performance of that reservoir. Then the second problem that we all faced as a petrophysicist when it comes to deep water is the thin bed and high water saturation associated with it. Most of the time, as I said, the turbidites, which are actually the most sought after reservoirs in deep water, can be associated with a lot of thin beds and lamination. When you have lamination, the resistivity goes down, and when the resistivity goes down, the water saturation is high. So when the water saturation is high, then it can happen two things. Either you can just rule out that this is not economical, this is not part of my net pay, so you just ignore that, or you may think this is not a good quality reservoir because the water saturation is extremely high, but that is not actual representation of the reservoir. So the way we actually solve this is to get a different type of resistivity measurement. Instead of standard resistivity, we can measure nowadays a vertical and horizontal resistivity separately, and using that information we can get a much better hydrocarbon saturation, which is a better representative of the reservoir than the standard one. So that approach helps us to increase the net pay when it comes to petrophysical evaluation. That helps us to increase the potential of the reservoir from formation evaluation side, which is the actual potential of the reservoir. So we can get close to that actual potential. So that's how we can solve this saturation issue. And then it comes to the issue of porosity distribution, or to understand the bound portion of the water. Again, this deep water deposit, as I told, it can be associated with silt, it can be associated with laminated sand. So all these reservoirs, they have a lot of water which is not going to produce or not going to contribute. They are not movable. They are actually bound water. So understanding how much water that what you have in the reservoir is actually bound and not going to contribute is a very important information to understand. And there comes the beauty of NMR type of measurement, which gives us not only a lithology independent porosity, but also gives us a fractional porosities, which is the movable fluid, irreducible water, or clay bound water. So the clay bound water and irreducible water, that doesn't move, that stays in the reservoir. So whatever the movable fraction is, if that fraction is filled with hydrocarbon, even if the saturation of water is quite high, so and all the water which is there in the reservoir is bound, so you can get a really water-free production even with lower hydrocarbon saturation. So that's the reason understanding of the bound portion of the fluid is very important in this kind of reservoirs, which is mainly infested with silts and laminated sand shell kind of area. So having these uncertainties reduced when it comes to porosity and saturation, we can integrate all this information to come up with the integrated petrophysical evaluation, which gives a better insight to the reservoir. So it gives all porosities and also give the irreducible water saturation, which is extremely important, that comes directly from the NMR. That is the reason we want to measure the bound fluid, because the bound fluid is the contribution to the calculate of SWIR, or irreducible water saturation. So that gives much more complete picture of that reservoir. And after that, you do need to have some formation testing to be done to understand the quality of that fluid that you are dealing with. What is the mobility, the gradient, the viscosity of the fluid, and you need to capture a sample at the end to get it, to make it a success, to show and to do the analysis for the future plan to develop this in the future. Okay, so this is the deep water formation evaluation workflow that well appreciated in many part of the world, and we also use it in with many operators with success, to give a better understanding of the formation evaluation of the deep water. So this is another very interesting matrix that we developed over the years. This is a value of information kind of matrix, where we wanted to understand the questions that a petrophysicist asked or an operator asked, to understand the reservoir. And then we wanted to come up with what are the solution that we can provide to the operator with pertinent to that particular question. Like, this is a very interesting slide, and we can have some time on this. So these are the questions that people generally ask. Where is the pay? In the deep water. That is a very basic question to start with, and you can see that's where I listed all the question. And after that, in different columns, you can see the solution that each and every service and each and every solution can offer based on the tool. So where is the pay? If that is the question, to understand that question, having NMR solution, we have the names, which is MagTrack is the name of our LWD tool, NMR, and MREX is the name of our wireline tool. So we have the name, and you also have the generic name to understand where it is. So NMR provide that kind of information by telling you where the movable fluid is. 3D resistivity, or the multi-component resistivity, which provides vertical and horizontal resistivity, that helps us to identify those thin beds. If the thin bed problem exists, if the resistivity is not that great in those kind of areas. So having a 3DEX kind of multi-component resistivity helps us to identify that. Okay. GXPL or EMEX, I will come into those things later, but the image log that also can identify those thin beds visually, just taking an image of that. Okay, then what are the fluid type? Okay, how can we get that information? NMR can be a very good tool to get the information of the fluid type to start with. And then the ultimate choice will always be the formation testing and sampling tool, which will provide you the ground truth to do the fluid ID analysis, which is a tool of choice for that. But yes, NMR provide a valuable information before you go for the formation testing. Using that 2D NMR approach, we can do a fluid ID, and based on that, you can select the suitable points to go for formation testing and sampling and fluid ID measurement. Then comes another problem of sand volume. What is the volume of sand? Again, NMR can provide a very clear clay-bound water measurement, which can then be used to calculate a clay volume. 3DEX provide laminar sand shale volume, which can be used to get the sand volume. And then the image is obviously a visual measurement, which also can be used to get the sand volume by doing a sand count kind of analysis. Then the bed thickness, the thickness of the reservoir. Image log is the tool of choice to get the accurate thickness of those reservoirs, because the image log is the highest resolution measurement you can get. The porosity obviously NMR is the tool for choice to get all different fractional porosities, not only the total porosity, but also the movable, irreducible, and clay-bound water. Movable hydrocarbon, whatever hydrocarbon that you have, how much is going to move? Definitely NMR is something that what you need to go for, because that actually measures what is the movable portion of the fluid. So even if you have a lot of porosity, if you need to know how much of that porosity is going to move anyway. Okay, fluid, and then suddenly the formation testing and sampling is going to confirm what type of movable fluid you have. Then the permeability. So where can we get it from? NMR can provide permeability. It's a model permeability, but certainly one of the most important tool for that is formation testing and sampling, which is used to get the mobility and the permeability. Then the hydrocarbon saturation. Again, it comes NMR and 3D resistivity. Interval to test or perforate. Again, we can use the combination of NMR and 3Dx. Then comes the formation deep and azimuth. Then obviously the image log is the tool for choice. Samples, definitely. You need to go for the proper sampling tool. If there is a problem with mineralogy, then you need to go for a mineralogy tool. That's what we call a rock view. And the depositional environment, I could not emphasize more how important that is for the holistic formation evaluation. Certainly, the image log is the tool for choice. And the clay typing, that is also important in some of the deep water deposit to know what type of clay we are dealing with. That poses a threat to drilling, that causes a threat to the development of the reservoir. And certainly, the mineralogical tool can provide a detailed idea of what kind of clay you have in the reservoirs. So this is a really important matrix that we shared with many of our operators, and they're really happy to. So it gives you a really nice idea under this matrix, what kind of problem and what are the solution that you can get from what tool to solve the problem. You know? This is, yep. Okay, so now we understand the problem, we define the problem, we know what are the solution. So now I'm going to talk about more on some of the solution and the tools that what we can offer to provide that solution. So one solved problem we discussed before is the thin bed problem. That means the resistivity of that reservoir when you have a laminated sand shell section is much lower than the standard what you have in that sand section. So let's say this is a cartoon of the laminated sand shell. Let's say if you have a sand and shell interlayered, and the resistivity of the sand is 10 ohm meter and that of shale is 1 ohm meter. When you put it in a laminated form and then you use a standard resistivity tool to measure, you will end up measuring somewhere in the range of, let's say, 1.8 ohm meter, which is much lower than the actual resistivity of the sand, because the hydrocarbon is there in the sand itself, it's not there in the shale. But the resistivity that you are measuring is definitely much lower than that of the sand layer. And if you use that low resistivity to calculate saturation, obviously you are going to calculate a lot of water saturation here, which is not an actual representation of this reservoir. So as a petrophysicist, we need to have something to come up with a measurement of that sand resistivity. And that where the three-dimensional multi-component resistivity makes a lot of difference. And it's one of the key tools of any deep water formation evaluation. As I said, most of the deep water formation is always associated with thin beds. So what it does, it measures a resistivity in two directions, these two. One is the direction which is perpendicular to the bedding plane. Another is the direction which is parallel to the bedding plane. The one which is measured parallel to the bedding plane is known as horizontal resistivity, and any standard tool measures the same. But the typical of this tool is the vertical resistivity. You can see that now it is much higher than the horizontal one, and it is reading in the range of, let's say, 5.5. So this higher resistivity, we can use both of them together to calculate the resistivity of the sand, which is, let's say, 10 ohm meter. And when you use that, certainly you will end up getting a better hydrocarbon saturation. which suddenly make this reservoir exciting for any formation evaluation or further interest. You know? So this is a log that what we can generate from 3D. So you can, the log you can see the first track is the gamma ray track and then the resistivity track. The red curve is the horizontal one and the green curve is the vertical one. So whenever you see a separation, that's where we call it, and it has got an anisotropy, and it happens when you have a laminated sand cell section. If the reservoir is clean, if you measure it in vertical direction or horizontal direction, it doesn't matter. It is an isotropic reservoir, so you can see that all the curves overlay on top of each other. But whenever you have a laminated sand shell section with hydrocarbon in it, we'll always see a separation, and using that, certainly you can calculate more hydrocarbon than using a standard resistivity log. So the additional hydrocarbon here that what we calculated is now the incremental, which is in a black in color. Using the horizontal resistivity or standard resistivity is green. It always happens like that. Very simple. You have a better resistivity, you calculate better hydrocarbon. So this is an actual case study from a deep water setting from Brazil. We have this kind of log in many places in Southeast Asia. We have used it in Brunei, used it in Malaysia, in Australia, some of the places. And we always have seen the similar type of thing, what we can see from this paper. The paper name is already written here. You can always refer to and later on can get it. The long story short, um, the Petrobras, they use a standard kind of resistivity, and obviously you can see this is a deep water turbidite deposit, so you'll always expect a good, nice, clean sand at the bottom, and then when you go up, this is the laminated section comes in, and the increase in shale is directly affecting the resistivity, which is going down and down and down. So you can always get a good hydrocarbon saturation here using any log whatsoever, any resistivity log. But when it comes to the top portion, using a standard log, which is blue in color, you see, we'll end up getting a lot of water saturation. Whereas when we started using 3DEX kind of approach, you can see the resistivity increase a lot. That is the actual representation, because you do have a lot of hydrocarbon, which is here, and the red color is the sand resistivity. You see the resistivity of sand should be very similar to that of the clean reservoir, because the same sand we are having in this laminated sand shell section. So that so actual that resistivity is expected, the similar type what you are getting in the reservoir. So when you use that, certainly the saturation increases. So actually, Petrobras published it that they added additional 40% reserve in that deep water play after using 3DEX in those kind of laminated section. So that pay was not previously calculated because this approach was not available at that time. So we have used it, as I said, in many deep water reservoirs throughout last 2 decades, and in many places this is a very standard tool for deep water formation evaluation, just to overcome the problem of low resistivity pay associated with thin beds, which is extremely common in deep water setup. Okay, so that was the 3D resistivity. The second approach, as I mentioned in my earlier slide, is NMR. MREX is our wireline tool, MagTrack is our LWD tool, but both of them are magnetic resonance and provide very similar type of solution. So NMR is very important. Let's look at the application first. This is a very important tool, as I mentioned, is to understand the porosity distribution. In deep water setting, there are many places where you have a lot of silt or laminated sand shell, and those areas are notorious of having a lot of bound water. So understanding how much water is actually bound is gives us the SWIR, or irreducible water saturation, which is an extremely important information in petrophysics. So that's the boundary, to understand that. So if there is a lot of bound water in those kind of reservoirs, even if there is a little bit of movable porosity, so you can actually flow that and produce that without any water. That is very important. So it gives those kind of different porosities. It gives a, it is a lithology independent porosity. That's another important aspect of it. It doesn't matter what kind of formation you have, which is something happens in density porosity, because you need to use a matrix density to calculate it, but it doesn't require that. It gives a permeability index later on that can be calibrated with a known permeability. It gives an immense information to select the formation testing point, where there is a good permeability, where there is a good quality movable porosity. Those are the areas that those are suitable for formation testing. So operationally, this gives a big input to that. Then fluid ID. Fluid ID is something which is very important, can be done on the basis of NMR data. I'll talk about it in my next slide a little bit more. So that also gives us a very big information to select the points for your formation testing and sampling. Before going there, you have an idea of what kind of fluid to expect. So 1D NMR and 2D NMR, that means the T2 spectrum, that is where we generally look at. So this is an NMR log at the right hand side. This is a very standard deliverable of NMR log. So I will just go through the log just to be easy for everyone to understand. The first track is a gamma ray. The important track is this one, where the resistivity is plotted along with the permeability. And then this is a density neutron, just to let you know, to give you an idea what to expect. And then the last track is the different types of porosity. The brown is the clay bound water, blue is the irreducible water, and the yellow part is the movable water. So that means once you have a lot of movable water, that's the reservoir, which is mainly important, where you have a porosity, which is mainly big pores, movable fluid is over there. So that's where the hydrocarbon resides. So these are the reservoirs, which is the main reservoir we should go for and we sought after. And this is the T2 spectrum that was I was talking about. That's what measures NMR measured this T2 decay, and from that T2 decay we get the T2 spectrum. So we can use this spectrum to do a fluid type of analysis. Generally, oil or gas or that kind of hydrocarbon, they comes much later at T2's time. That means towards the right hand side, and the water which generally comes a little bit earlier, that means towards the left hand side. So you can look at the T2 and that gives an idea about the two, about the fluid type. That is pretty well, especially when we use a single frequency acquisition, that is our LWD NMR tool. But when it's a wireline or multi-frequency acquisition, we need to do a little bit more, like a 2D NMR type of approach. I'm going to talk about it in my next slide. That is needed to do a proper fluid ID application. But yes, even here you can see that there is a shift in the T2 spectrum that can be interpreted as a change of fluid, and you can use that to identify what is your contact, where is the expected contact. Okay, so that's the NMR analysis or NMR log that we use to do that kind of analysis. So the tool wise, yes, I will go back to the tool now after talking about the application. So yeah, MREX is our wireline tool. It's a multi-frequency tool. And yeah, we acquire the data in the single pass and do all the fluid typing and all analysis that is important for formation evaluation. We also have that in LWD. We call it MagTrack, and it provides also a very similar type of solution, and also it provide that information real time because you are acquiring it in LWD while drilling. So also two unique application that what we have in NMR that is also can be quite important is NMR also provide, we can process the data to get a grain size distribution analysis. Not everywhere you get a core, so core is costly. Not every reservoir is cored. So NMR is something that can be used to get an analysis of the distribution of the grain size, which can be very important in the places where you have a sanding type of issue, or you need to use a screen to do that. So core generally is taken in only one place, but because NMR is a continuous measurement, so having that information continuously, grain size analysis can be very suitable for those kind of areas. It can also be processed to provide synthetic capillary pressure, relative permeability, and a productivity index. So this is another a quick interpretation that can be done before planning for a costly DST kind of application. It's a deep water. Having DST is extremely costly. So having an NMR log and then quickly process it to get an idea about the productivity index of those zones can be very, very handy to do a planning for the DST. So that's how NMR can help in terms of deep water formation evaluation. So I have one dedicated slide for the fluid ID because that's something we always do before formation testing when it comes to deep water. So you use because MREX is a multi-frequency acquisition, we acquire diffusivity as well as T2. So when we plot diffusivity and T2 in a map, that's why it's called 2D, then the different fluid types actually get separated. This is the line where we expect all the water because the water diffusivity doesn't change whether it is in clay-bound water or reducible section or movable section. T2 changes based on where exactly the water resides. Generally, the clay-bound water T2 is low and the movable T2 is high. So here we expect the water. And now this is the place where we expect the oil to be. Depending on the quality of the oil or the density viscosity of the oil, the diffusivity changes. So light oil generally comes with higher diffusivity. That's why you can have it somewhere at the top. Whereas with the increase of the viscosity of the oil, the diffusivity decreases and you can expect the heavier oil towards this side where the diffusivity is low. So this is how we do a fluid typing. This is a very important one, and pretty much we do it every time whenever we run NMR to provide an idea about what type of fluid to expect. And that also gives a very important information for the petrophysicist to plan the formation testing and sampling points so that he or she knows exactly where to look for. This is how it looks like. This is an actual data. You can see the oil is in the oil line. We call this oil line, and this is how the water is. Sometime, not sometime, pretty much most of the time, these deep water wells are being drilled by oil-based mud. So that can cause a little bit of problem because when you have a light oil and oil-based mud filtrate exactly in the same place, there can be an issue where that whether can be identified or not. But yes, if these two oil are separated in terms of um, its composition, then certainly their diffusivity and the T2 will be separate and we should be able to identify them separately. We have done that in many times, and this is actually a picture from one paper that we published. So yes, if they are absolutely same in terms of properties, obviously they will appear in one place, but as long as they are having two separate type of oil in filtrate domain and in the formation oil domain, certainly we can distinguish them properly. So yes, this is an approach we take to do the fluid typing. And in the previous slide, I explained what we actually do with the NMR data to solve the petrophysical problem. Okay, so those are the formation evaluation problem that based on those two formation evaluation line that we talked about, 3D and resistivity and NMR. But now comes to the area where we need to integrate the formation evaluation with geology. As I told you, it's extremely important to understand the geology and the geological setting. And to understand the geology, we need to have an image log. That's the log we want in terms of geological interpretation. So the two important tools that we regularly use in deep water setting is what we call GeoExplorer. That's our oil-based mud resistivity oil-based mud resistivity imaging tool, and our new generation, which is a very new tool, which is Enhanced Imager Explorer, which is the next generation of the old tool. Those are the two resistivity tools we have used in the Southeast Asia and the whole world in many deep water setup. So In that, this is what we expect from an image log. We expect a nice image, and those image can be processed in static and dynamic mode, which are to get a better contrast in dynamic mode. Static is mainly to have an overall idea about what type of formation what we have, and to understand the formation a little bit better. To get a better contrast, we need to have a dynamic image. So this is a comparison between the GXPL and Emacs, which is our new tool, better and higher resolution tool. Certainly it has got better resolution, so the thin beds and small features can be identified very sharply and easily. So it's a pad device, so you can see those 6 pads, six images, which is coming from 6 different pads that you can see from this image. But also we can put two tools together, which in a dual mode, to improve the borehole coverage, especially in the larger hole section. So yes, this is the image that we need to acquire, and that's the basic data to start with. And after that, we can do a lot of interpretation work on this image to get a detailed idea about that depositional setting. So these are the application as we talked about that we can get from the image log, starting with dips and strikes, then fault and fractures if that is present, then sedimentary and stratigraphic interpretation, structural mapping, then goes to depositional environment and well-to-well correlation. That all can be done using the image log, which is a very critical element of formation evaluation when it comes to deep water. So this is an example of how an image log looks like, let's say in a turbidite sequence. So this we had a core in that well. We had image log, and this is a cartoon to make you understand what this image log is related to, what kind of geological setting. So this is the bottom currents where you have all this laminated beds. Then there is a debris. So you can see the debris in the image log. You can see that in the core as well. And after that, then the turbidity current with the cleaner sand at the bottom. That's why it's brighter in color. And then then it goes a little bit siltier at the top. That's why the color also changes. Same thing is happening. You can see the core in the image. They match very well. And that's the thing. You may not get core every time, but you can produce a similar type of information from the image log, and whatever interpretation you can do. Obviously, there are certain interpretation which you cannot do with image log, that only can be done on core. But when it comes to facies kind of or lithofacies kind of application, image log can be a very handy information to have, even if you do not have a core. It can provide a very detailed facies analysis, and that can be extremely useful for the formation evaluation in deep water. This is the image interpretation workflow that we always follow. Obviously, start with the data QC, and then start with the basic processing, and then the deep computation, structural analysis with the workout plots to understand different structural zones. And then we use the net to gross, which gives us an idea about the thickness of the sand, or the net sand count. And then comes the sedimentological and sediment dispersal analysis, and with that, we come to a depositional environment and reservoir architecture kind of interpretation. So yeah, all this information, which as I said in my first couple of slides, are extremely critical to have a proper formation evaluation. So those are the discussion on the image, 3D resistivity and NMR. Another critical element, not everywhere, but sometimes it can be really important to understand the mineralogy. Not everywhere, but as I said, if there are some critical, complicated mineralogy that needs to be understood, and that is causing some uncertainty in the information, in the interpretation, then we do have another option to go for the mineralogical solution, which we call rock view. And we include two tools in that. One is formation lithology explorer, that is induced gamma ray, and another one is digital spectrolog, that is measurement of the natural gamma ray. So truly speaking, we use an electronic pulse neutron source for that flex. So you bombard the formation with this pulse neutron, and then it interacts with different elements, and then causes then that interaction produces a gamma ray, and we measure the gamma ray, and from that spectrum, uh, there can be different interactions starting from it can be an inelastic interaction, and after that it loses its energy and go to further and then get captured by some of the nucleus of that element and then release another set of gamma ray. That what we call as capture spectrum. Two different spectrums provide a list of elements. From there you can see that the list, so we can get a lot of elements from capture spectrum and inelastic spectrums. The elements are written here, like aluminium, carbon, iron, magnesium, silicon. Those are coming from inelastic, whereas calcium, iron, magnesium, silicon, these are coming from capture. And the natural spectrum provides thorium, potassium, and uranium. So using all these elements, what we can do is come up with a mineralogy. So if you see, this is actual log from there. All these elements are plotted in different colors, but at the end, we come up with a different mineralogy of how much quartz percentage is there, and if there is any carbonates associated with it. So this happens time to sometime when you are dealing with pelagic sediments in the deep water. So suddenly you have some amount of carbonate suddenly. So that can also be identified in detail. If there is a lot of feldspar that needs to be identified, which causes a problem, then that can be identified here. Another very important aspect of it is a clay typing. Sometime understanding of what type of clay you have in the well, whether it's a swelling clay of smectite or a kaolinite or illite, if that needs to be done, because it measures all iron, magnesium, aluminium. You can get a detailed clay typing done using a rock view service, and that can be very critical in some of the wells if that's something which needs to be understood in that particular area. So yes, this is another important service. So if that is the problem you have in the deep water setting, so this is the service to go for. So those are all formation evaluation challenges. If you have a challenges with porosity, NMR, challenges with saturation, Friedrichs, geological uncertainty image, then mineralogical uncertainty, then rock view service. But at the end of the day, after uh, a success of a well is always dependent on what kind of fluid is there. So understanding the fluid, identification of the fluid is extremely important. Yeah. So logs can provide a decent idea, but definitely the ground truth always comes from the formation testing and sampling. And there we have a different sensors to use to identify the fluid. Yeah. So the two things that what we use is what we call a sample view, and the next generation one is what we call IFX, or In Situ Fluid Explorer. What it does, as you know, in any formation testing tool, you have a probe which you place on the formation and you suck the fluid out of the formation. Once you get the fluid up from the formation, you just pass it through different sensors and keep on measuring different properties and use those properties to identify what kind of fluids you have in the channel, what fluid you are actually sucking out of the formation. So first always is the near infrared spectroscopy, and that is important to identify what type of fluid. So all this information actually leads to the identification of the fluid. So in that you have near infrared measurement that has hydrocarbon channel. So it gives us an idea of what if there is a hydrocarbon. So let's say you are trying to sample oil in a water-based mud. So you always start with like water filtrate, and then you suddenly get indication of hydrocarbon in that dedicated channel. You see truly this is how the liquid flows through. It goes through this sapphire window, and you use an optical light which is in near infrared. It passes through that fluid, and the fluid absorbs certain portion of that light and let go certain portion of it. Based on what type of fluid you have, you can get a different type of absorbance. And we monitor the spectrum when there is a wavelength and there is an absorption, the graph. So different type of fluid has different type of absorption, so we get the information in different channels. So water has got a specific channel, it absorbs specific wavelength of light, and oil absorbs a specific wavelength of light. So once we analyze the spectrum, we can get the information. We also measured the refractive index. It's quite important, especially when you are sampling water in water-based mud. Well, obviously, the refractive index will change when you move from one fluid phase to another. And that change is important to understand when the filtrate is done and you are seeing now the formation fluid, and you can identify the formation fluid. We have fluorescence, so that means the UV spectrum. So as you know, there are certain part of the certain hydrocarbon which fluoros, so it gives us an idea, okay, this is the hydrocarbon. And then in situ fluid explorer, which is our latest generation, we added a couple of more sensors. One is the tuning fork, another one is the sound speed, and both of them are used. The tuning fork is used to get the density and the viscosity, whereas and it also helps the permeability calculation. And sound speed is like an acoustic transducer, so there are different sound speed depending on what kind of medium you are. So having all this information can be extremely useful when you are doing a proper fluid sampling, because identification of the fluid when you are going for a deep water well, extremely costly well, very costly drilling affair, to identify a pure what kind of fluid you are dealing with is extremely important. And not only that, the reason you need to identify the fluid is actually to get a proper representative sample, because the problem with any sampling tool is obviously the first phase that is going to flow is the filtrate, because when you drill the well, there will always be filtrate. So to understand the contamination level, to capture a very clean sample, you need those kind of extremely sensitive sensors to know when the filtrate is ending and when you are getting formation fluid. Not only that, that's a very generic statement. Obviously, you need to know what is the contamination level, because that is very important when it comes to analyzation of means when you wish to analyze those samples to do a future planning. So that's where this focus sampling technique is extremely important in deep water evaluation. That because you do not drill deep water wells frequently, you get one or two chances, and then you need to be extremely sure that you are collecting a very pure and good quality sample. But there are other things, because to clean you need to stay a longer period of time, and spending a long time in a deep water well can be extremely costly. Also, if you be stationary there for longer period of time, there is always a problem to get stuck. Obviously, nobody wants to get stuck, and that can be an extremely costly affair again. So this is a solution that we bring in. We call it focus sampling. So instead of having only one nozzle or one gap here, this kind of approach has two gaps or two areas or two inlet. One, the middle one, what we call that's the fluid line, and the outer one is called the perimeter line. That's for the mud sampling. What it does, it using a different type of pumps, two different pump rate, we create two different type of drawdown, and so that the mud filtrate goes faster through the perimeter line, and which goes down, let's say, and then that would be much easier for us to clean up and get the fluid for representative fluid through the fluid line which is in the middle. So this kind of approach, in the focus sampling approach, helps us to clean faster, and it helps us to get a cleaner, faster sample, safer sample, because you need not to spend a long time in the borehole, and you always get a much less contaminated sample using this. So that's how we are using both the IFX and focus sampling in many of the deep water wells to monitor the cleanest point for sampling, to get a proper idea about what fluid you are sampling, and then sample it faster and cleaner to get a proper representative sample of the well. So that was all about different technology that I wish to discuss. And I wish to conclude this talk with a very interesting question that I always get in many times in many operators. Generally, if the well is not success, many cases people tend to cancel all the logging. So this is a question we always get. I always get means, shall I cancel all my logging? This is not a successful well. So should I cancel? We don't need any data because the well is not successful. I believe this is a very interesting point to be discussed as a community. We personally believe that it is not a very judicial way to do it. We call it a concept of geological logging. So when there is a no success, so there can be different reasons for not success. There can be, let's say, no reservoir. That means the geological uncertainty is quite high. So the geological or geophysical model that what you are using to select the location of the well has got a lot of uncertainty. So that means that uncertainty needs to be reduced, and the VSP and acoustic kind of data can be extremely important to get the velocity right, to do the to fine tune the geophysical and the geological model in that. It can also be Image log can also be helpful extremely to fine tune the geological interpretation that what is being done. Or, okay, the next question can be it's not success because no hydrocarbon. So again, that can be a big geological uncertainty. And then that means we have found the reservoir. So geophysical uncertainty is less, but the geological interpretation has certainly got some uncertainty. So having an understanding of the geology can be extremely important, and running image log can be quite important. And then it can be a not success because the desired hydrocarbon is not there. So again, it's all type of this problems are associated of geological uncertainty. So we need to have a proper geological logging that needs to be done even the well is not a success, so that the next well you are planning to drill have a better success ratio. That you expect to be a better success when you reduce all this geological uncertainty. And another thing can be not enough thickness. So we have a reservoir, but the thickness is not enough. So that's the reason 3DEX can be extremely helpful. Probably it is there, it's just the tool that you are using is not sensitive enough to give you a proper information about the extent of the reservoir. So having 3DEX type of analysis or information can be extremely useful in that case. So that's actually a very interesting topic I wish to conclude my talk on. So this is just a summary and the conclusion. So let's accept that deep water deposit involves a complex geological process. So the formation evaluation is challenging. So that is something as a formation evaluation person, we need to understand and accept that it is challenging. So acquiring correct and adequate data is absolutely necessary. Otherwise, if we keep on acquiring standard triple combo data, non-adequate data, then we will just keep on talking about the uncertainties, but we live with the uncertainty. We will not be able to reduce them. So that is very important to acquire adequate data in a deep water setting. But yes, we always wish to run everything, but we understand there is always a problem of budget. So that's the reason a key well concept is extremely essential. That means you dedicate one or few wells depending on where you are drilling it as your key well or science well, where you do not think twice while acquiring data. Acquire as much data as possible to understand the complexity of the deposition, to understand the issues that are associated with that reservoir. And then once you reduce the uncertainty, you can minimize the formation evaluation program. But at least those key wells, those science wells, we need to have an adequate amount of data to understand the reservoir properly. So then the next point is understanding the reservoir architecture. So not only a formation evaluation, as a petrophysicist, we mainly discuss about the porosity, permeability, saturation, but that is definitely needed, but that is not the end point. That petrophysical interpretation needs to be associated with the geological interpretation. So acquired geological data is important, and having that link is extremely important in deep water. And as I mentioned, advanced technologies are needed. 3D resistivity, NMR, mineralogy when it's needed, efficient formation testing and sampling. These are all important part of deep water formation evaluation. And then last but not the least, yes, if the well is dry, still it is advisable to acquire geological data, because there is a reason the well is dry. That means there is uncertainty in the interpretation, and we need to reduce the uncertainty in order to make the next well as a success. So that's what I wanted to discuss. I've been speaking a long time. Hope everyone is still with me. But this is what I wanted to discuss, and that's from our experience dealing with a lot of deep water wells. So I'll stop now, and feel free to ask as many questions as you wish.
Okay, all right. Well, thank you, Mr. Saikatas, for the very fruitful and comprehensive explanation about the deepwater formation evaluation. And I assume that the enthusiasm from the participant is quietly high today, because there are almost 100 participants we have today. And we appreciate your spirits, ladies and gentlemen, to have this technical discussion in this Saturday afternoon. And before we jump out to the question and answer session, I would like to remind to all of the participants that you can participate in our discussion today by asking your question in the chat box by following the format, the name, underscore affiliation, and underscore question. So, sir, we have several questions in here, and we would like to start one by one. The first question is from Pa Andang from ISPG. Do you have examples of highlighting the response difference between LWD and MR with MREX in the same section of deep water well?
Sorry, I could not understand the question properly. Can I read the question in somewhere in a chat
Yes,
box?
you can
Okay.
open the chat box. Yes, in the
Okay,
middle.
let me
Yes.
open the chat box. Yes,
Okay.
okay, okay. Yeah, I think that is a easier way of doing. So you
Okay.
said, okay, do you have examples highlighting the response difference between LWD NMR with MREX in same section of a deep water well? We do have, yes, in certain places we run both the tools together. So in general, the big difference between the LWD NMR and the MREX, which is wireline tool, is the way we acquire the data. LWD NMR, we acquire it at one single frequency, whereas in MREX, which is our wireline tool, we use it a multi-frequency acquisition. So the spectrum that we get are technically very different, because multi-frequency acquisition has that means we are having a magnetic gradient. That's the reason that is a more of like an apparent spectrum, whereas in single frequency the magnetic gradient is very low, so that spectrum is more like a very similar to like a T1 spectrum. So you have more sensitivity in that kind of spectrum when it comes to different fluid type. But yes, we can share a few papers on that. Both of them has got its own advantage and disadvantages. LWD, because we acquire the data while drilling, we need to minimize the drilling noise, whereas that's the reason uh, we cannot have a multi-frequency acquisition because of the diffusivity issue. Whereas in wireline, with the environment is very quiet and calm, so we can have this multi-frequency acquisition, so we can measure diffusivity and use it for a better 2D NMR type of fluid typing analysis, and to run the log faster as well. So I hope I answered the question.
All right, sir. The next question we have from Pak Harwi. What is the best practice to ensure the maximum ultimate recovery achievable, particularly when the thinner limited beds happen to be in the upper part of the reservoir?
Okay, maximum ultimate recovery, then that's more of a production related question. I'm not the best person to answer that, but certainly from a formation evaluation side, we need to, our job from that aspect is to make sure that we know that those laminated sand cell section which is at the top are hydrocarbon bearing, then to include that in our net pay calculation, so that we, from the formation evaluation side, we have a better representative net pay calculation, better saturation calculation that's done using for against the total uh, reservoir section, not only just the clean sand at the bottom but the top part as well. Once that is done from the formation evaluation side, certainly the production technologist will be a better person to answer this, how to ensure that we get as much as we can from the whole pack rather than the clean part. One thing can be just from an experience we can say that, let's say if you do not know that the top part is also a good hydrocarbon bearing section, you may probably bypass that part and just focus on the clean part, and that the reason we see a lot of bypass hydrocarbon in many old wells where the thin beds were not identified at all. So we will identify only the clean section and produce the clean section, and we didn't even know that the thin beds were there which were cased. So nowadays in many operators, even we are working together with a few of the operators to do a behind casing opportunity hunt to reprocess the old logs to find out where the thin beds are, and then go ahead and do a cased hole logging to identify those zones and perforate those zones which are has got potential, and then producing it from here. So yeah, probably I haven't answered a direct one-to-one question, but as a formation evaluation person, that's what we can bring in the table.
Sir.
Hello.
Okay.
Hi.
Uh, yes.
Can I elaborate a little bit further, please, for my
Oh,
question?
yes, please, Pak Harun.
Okay, Mr. Saikas, thank you very much for interesting presentation.
Yeah,
In
thank you.
fact, that's the questions from especially from the development people, especially when we talk about the thin beds. My experience in North Sea that we got inter-channel deposits, which are thin beds. And in fact that the production is not very high. The well flow is not very high as according to your graphic, but it is indeed the well still producing very long time. Now, the well was vertical. Of course, the question is based on this very much detailed analysis with your tools. Actually, we can pinpoint the reservoir much better. And then, of course, production technologies is able to design the well appropriately. Now,
Okay.
my question is also regarding whether this thin bed is really contributing to the flow.
Truly speaking, yes. We obviously this is a very specific question for a very specific field. So I may not be able to give you a correct answer for that pertinent field. But in general, that comment is, that's the reason we need to understand the geological setting. That's the whole reason I was emphasizing a lot in the beginning. So just only petrophysical evaluation of the logs may not give us this insight, but if we include our petrophysical evaluation along with the geological knowledge, image log is one, but suddenly we can incorporate as much information as possible, literature, field knowledge. So if that setting gives us the information that this laminated sand shell sequence is extensive, it is a much larger extensive, like when you keep on drilling more wells, you can certainly do correlation and keep on mapping the extent of those thin beds. So those are the information which is very critical to have an idea that these thin beds can be producing really, really long time. But if that thin beds are now, once we understand the geology and we interpret these thin beds are not associated with that kind of deposit, it's not a sheet kind of deposit, probably it is just within an MTC or something like that, and it's not continuous. So those thin beds are certainly not going to produce for longer period of time. So formation evaluation wise, that information we can certainly bring in, incorporating from petrophysics with geology. And then the production technologies, they may certainly come up with their own way of giving us information. So that's my answer to that.
Okay, thank you very much.
You are always welcome, and very interesting question.
Okay, thank you to Pak Hargianto and also Mr. Saikatdas. We are move on to the next question, sir, from Bapak Andang from ISPG. How extensive is the huge catalog of basin-specific mineral model?
Okay, so in our mineralogical, as you know, okay, so we measure elements. So element, and from elements we interpret minerals. So certainly when we start in one basin, the interpretation needs to be because there are possibilities are much more, it's like any geochemical kind of analysis. When you start with elements, you can come up with more than 2 or 3 minerals with the same elements. But to understand the geology, understand the basin, gives us a framework that which mineral association is possible and which mineral association is not possible. So that's the reason this is like a smart system where we can tell that, okay, this is not possible, so do not calculate that mineral. So, or this mineral is suitable and you calculate that mineral. So that kind of basin specific model we can always do because it's a smart system. The possibilities are limitless. So if there are few minerals which is absolutely not possible in that setting, we'll just not calculate it. So that's how we work in terms of interpreting minerals from elements.
All right, interesting, sir. And we
Can I
also
answer
have,
my question?
oh, yes, sir, please.
Uh, yes, I refer back to the first question that I posed there about the the Lw Nmr and also the MREX. Is so if you said that the Lw Nmr has just only one frequency to be taken over there, so what is the importance of the Lw Nmr then?
Oh, okay. Yeah. So yeah, it's a very interesting question. So LWD NMR. So number one is like some places it's not possible to do wireline. In those complicated wells where we cannot do wireline, those are the places we, and operator is asking for NMR type of solution. So then LWD NMR is very important because you just cannot do wireline in those areas. Number two, the reason where people ask for LWD NMR is to have an idea of real-time, like there is no wireline program at all. So you get a real-time porosity distribution and using that information while coming out, you do a formation testing and sampling run in LWD itself. So those are the areas where we are using LWD-NMR extensively. Third application, we use LWD-NMR where the sourceless porosity is needed and density neutron is not preferred, and NMR is a sourceless porosity solution for porosity. So in that case, yes, LWD-NMR provides very similar type of information. The single versus multi-frequency, these are it comes in a different reason. Multi-frequency acquisition has got its very own advantage, especially when it comes to fluid typing. Using the diffusivity is quite unique in 2D NMR that we can all get from multi-frequency acquisition. In LWD NMR, we cannot do that because it's drilling, like if the fluid measurement area that needs to be more in LWD. So otherwise the drilling noise, the tool is vibrating. So if the area is quite small, which is in case of wireline, but it doesn't matter because the acquisition is in very quiet and calm environment. In contrast to that, LWD, the tool is moving, vibrating. That's the reason we need to have a measurement area which is farther, wider, and that's the reason we use one frequency. We cannot measure diffusivity, but we still can be using that spectrum to do a fluid typing for lighter oil and gas. But unfortunately, we cannot do it for heavier oil just because of we cannot measure the diffusivity. But still, it works fine in light oil and gas. So yeah, those are the application of LWD NMR, if that's what you are looking for.
Well, how about that, Bapak Andam? It's clear enough.
Okay, I'll buy it. Thanks a lot.
You're welcome.
You're welcome. Okay, ladies and gentlemen, I assume that the curiosity and enthusiasm from the participants is quite high. So maybe I could offer to all the participants who already asked the question to ask the question directly to Mr. Saikat or not. And the next question we have from Pak Rona Siregar. Pak Rona Siregar, do you want to ask your question directly to Mr. Saikat, yes or no?
You can read it out. Thanks.
Okay, thank you, Pak Rona. And the next question, sir, from Bapak Rona Siregar. There are two questions here. The first one is, are those tools capable to hostile environment and especially formation testing and NMR tools?
Okay.
Maybe I suppose it refers to the tools that you have discussed in NMR.
Yeah, so when you say hostile environment, yeah, that's at a broad range of environment. But yeah, I can give some example. Yes, those tools. If you are referring to LWD tools, certainly those tools are made to withstand drilling environment. So yes, and we are using it quite frequently. So yes, so they are certainly capable of withstanding drilling and still gather good quality data. But yes, I need to be honest, but if let's say the whole condition is a problematic one, you suddenly encounter a huge washout section and it is beyond the measurement limit of the tool, certainly it will get affected, no doubt. But as long as it is within the measurement range of the tool should be able to perform quite well. Formation testing, same
Mr.
thing.
Saika,
Yes, please.
I mean, the hostile means what is the maximum temperature in degrees Celsius?
Oh, okay. The temperature. Our LWD tool that is rated for 150 degrees C. So if it is not a high temp tool. So if it is a high temp environment, yes, unfortunately, this NMR and formation testing tool, we do not have it yet.
How about the waterline?
Wear line is also rated to 350 degree for our MREX, and there it can formation testing can go a bit higher. But what temperature you are looking for?
Above 175 degrees Celsius.
Oh, in those cases, NMR won't. We do not have an MREX available for that temperature rating. Formation testing, there are certain ways of doing it, but yes, we have to have this a dedicated session for that if you have that kind of application.
All right,
But
thank you.
All right. And this the next and the second question, I assume that is the follow-up question. What is the minimum mobility for pumping out and sampling?
can't exactly remember a number, but we actually managed to capture a very high viscous oil, and we actually had a paper on that. If you can send me his email ID, I will forward it to him personally. I think that would be the better way of doing it rather than giving a number which I cannot remember at present.
Appreciate. Thank you. Second.
I will do that certainly.
All right. Pak Ronald Siregar, maybe you can contact the committee if you want to follow up these matters.
Sure.
We'll follow up to Mr. Saikartas for this. And the next question, sir, we have the question from Bapak Yulianto from PHM. Bapak Yulianto, if you want to ask your question directly to Mr. Saikartas or not?
I can read the question actually. The question is very well written. Could you
Okay.
elaborate the relation of pseudo PC curves derived from NMR? Do you have an example? Yes, we do have a paper again. That would be a better way. I can certainly send this paper to him. Uh, yes, so we have done this. So the way we calculate PC curve from NMR is obvious. You can understand the pore throat size, which has an important factor to play when it comes to NMR relaxation. So there is a way to model that with T2 relaxation uh, to PC. There is a relationship between the T2 relaxation and capillary pressure. And based on that relationship, we can calculate PC. And yes, we have do a comparison between the PC calculated by NMR and the PC which is measured from core, and I will certainly send a paper to him for him to understand the process properly.
All right. Still from Bapak Yulianto, sir. There is another question. If we have the series sandstone in rich conductive mineral such as chloride, glauconite, siderite, and pyrite, could the Tridex tool can help
If
us to
we
obtain the
can
true
have a shelly sandstone rich conductive minerals, could the trikes obtain the true resistivity of the sandstone? Okay, so certainly if there is a conductive minerals which is present in the formation with large numbers, then it will affect the measurement of any resistivity tools. No doubt. If it is if it is not in such a huge number, certainly the effect will be less. Absolutely valid question. If you do have a lot of conductive minerals, the resistivity will definitely be lower based on the conductivity of the mineral. Do the NMR will be affected by those conductive minerals? So actually not the conductivity part, which is important when it comes to NMR. NMR, as you know, that it works on the physics of magnetism. So if there is a um, ferromagnetic mineral which is present in the formation, what it does, it creates an additional magnetic gradient, which is not exactly by the tool. The tool expects the magnetic gradient to be something which is specific. But if you have a lot of ferromagnetic mineral, which creates an internal field gradient, an external, basically as additional one, which may have a effect on the T2 measurement. But again, if it is only few, we have logged it in many areas which has got some siderite and pyrites, but the result is good, no problem at all. But if the concentration of those minerals are higher, so that it affects a lot, then suddenly you can expect some issues with the NMR application in those areas.
All right. To Bapak Yulianto, it is enough or not? Or you have another follow-up question regarding the answer from Mr. Saikat?
Yes, thank you, Zaikat, for the answer. Uh, Many thanks for that. So I am interested to have the paper telling that we can derive the capillary pressure from NMR.
Sure, I will definitely send it to you. But could you please help me to get the email so that I can send it to him?
I gave
Okay.
to Wu.
Maybe you can, Bapak Yulianto, you can write down your email in the chat box. So I'll make that
Oh,
up
okay,
to Mr.
okay.
Saikat.
Or what I can do, I means if means I don't know, you have my email ID, isn't it? It will be easy if, okay, let me do one thing. I can write my email ID here so that everyone can see,
Yeah,
and
okay,
then
good.
It's better, sir. Thank you.
so it's okay, I'll make it bigger. So this is my email ID. So if you have any question and queries, please send the email. I will definitely respond. It's my name at bakerhughes.com.
Thank you very
Okay,
much.
thank you very much, Zaikat.
You are always welcome.
Yeah.
Right, sir. We move on to the next question from Bapak Harwi. In surface environment, my geologist, RE, and petrophysics college found that the low resistivity thin sand contributed to overall production and can be demonstrated by production, material balance, and history match. And the question is, are your tools also effective and optimum for the reservoir geologic environment?
Well, that's a very big question. I have to read it. My Ari and Petrovic colleagues found that the low resistivity thin sands contributed to overall production and be demonstrated by production, material balance, and history map. Tools are effective and optimum for the reservoir geology. Okay, so it actually he is actually telling that it matches. Yes, absolutely. Are your tools also effective and optimum for the reservoir geological environment? Absolutely. That was one of my most important point in the beginning. That the image log that are very important and helpful to understand the geology in a micro level, because we start with the seismic, you start with understanding of the geology, you build a geological model, but the resolution of those measurements are definitely not high. It has got a larger areal extent, but when it comes to a resolution in terms of depth, image log is a very high resolution measurement, so you can understand the variation of the reservoirs much better when you acquire few image logs. So once the way people, the geologists use image logs, they get the information from it and then they incorporate that in their geological model. So, and refine the geological model as we progress. So if we acquire in one well, then the next well, then the third well. So as long as you acquire more and more image log, you can understand the diversity of the geology in that reservoir more and more. So that's the way to do it. And I agree what you comment. I'm happy that you are mentioning that it agrees with your history matching and everything. So yes, I think we have done this as many times in the past, and that's the way to go. As the I think that's one of the most important point that I mentioned in my earlier slides. Deep water has very complex depositional environment, so it varies. So having a geological model, a simple geological model, may not be a good answer to all questions. So you need to have a more complex models, and that can only be done with a geological logging such as image log.
All right, Bapak Harwi, do you have any follow-up question regarding the answer from Mr. Saika?
Yeah, maybe a little bit more. Sorry, thank you very much again, Mr. Saikat. Yeah, this one is, of course, it's not deep water, but deltaic with a shore face.
Okay.
I think that you have already answered a lot. And I'm not geologist and I'm not petrophysicist, I'm geophysicist. So I'm still intrigued that quite a lot of time this kind of reservoirs is not only low resistivity but also not resolved at all by the logs, but yet that it contributed to the production. And then whatever you do, then it is not easy to history match or to make a correct material balance, because it's always something that not accounted. But when including the rather excessive kind of production in this case, it means more than the normal kind of reservoir. So that's why it comes to this idea. And of course, the resolution, the unique resolution about this contributing yet very thin reservoirs are important to take into account very much in detail indeed.
Agreed. I 100% agree with you. You know, it's thin bed problem or low resistivity thin bed problem. It's not a new problem. It's been there for a long, long time. And the people used to produce from here, from those reservoirs even long time back without having the aid of image log or 3D resistivity or NMR. Still people produced. It is like that. Then you depend on your luck a lot, you know, because sometime you may get lucky, as I said, and sometime you may not, you know, depending on what is the setting of those kind of thin beds, you know. But for the newer wells, we have the privilege, especially as we mentioning about deep water. It's always an extremely costly affair, so it's difficult to depend on the luck more rather than having an adequate data to understand and predict. So that's what I mean. I think we are telling the same thing. I'm just supplementing few of the information that you have already shared. I think we share very similar type of knowledge about that and understanding about that.
Okay, if you may, that I like to have another question, especially on the deep water then. Deep water depositional environment one is I mentioned already in the interchannel, but this one is actually from deep water Sabah, where thin beds or sheet-like kind of reservoir coming from the very distal of the turbidites. And that's really giving a lot of headache. And unfortunately, at that time that we could not continue to develop because of the excessive economic, the prohibitive economic situation that cannot develop this kind of field, because it's not very large, but the reservoir is also very difficult indeed. So is there any difference between interchannel as well as and this kind of laminated beds?
Yes, obviously. Now you are talking about the deltaic deposit. So deltaic
No,
deposit.
sorry. This one is deep water. Still, one is a very distal kind of turbidites, So it means that it's already becoming sheets rather than
Yes.
loops and so forth. Yeah.
Mhm.
And the other one is interchannel turbidites as well. But it means that like beyond the talus.
So yeah, so definitely means depending on where the thin beds are. So the distal portion of it, it's like now the grains are getting smaller, and you are already at the distal part. So the extent of it can be a bit restrictive, whereas inter channel area, those can be quite promising. That's what I can understand. So suddenly that is more of a reservoir related problem rather than a formation evaluation. But the information of whether it is in the distal part or whether it is in interchannel, that kind of information, if we can get and incorporate from the image log, that can be one information as from formation evaluation side we can bring in. But which one is going to produce more prolifically, it needs to have some a little bit more information than just a log. Suddenly some production logging, some DST information, that or complete well test information, those information can be really valuable and needs to be incorporated as well.
Thank you very much indeed.
You are always welcome.
Thank you, Pak Haryanto, for the very interesting discussion. And next, sir, I think this is the additional answer from Mr. Samir Dar. To add to earlier answer on predictability of thin beds, it is confirmed from post-production of RCI and PLP logs. I assume that it refers to the previous answer
Yeah.
about the
Yeah.
predictability of thin beds.
Yeah, I can certainly. There's, obviously thank you, Mr. Samidhar, for this. Yes, absolutely. So, obviously, this is formation evaluation. This is one step. The next step will always be to do the formation testing and the production logging and do the DST and well test. So, definitely, before we go for a development of a field, those steps needs to be followed through. Only formation evaluation is just a starting point. Then that needs to be validated with a proper formation testing, drill DST, well test, PLT, whichever, whenever is suitable. I 100% agree with him.
All right. And the next question, sir, from Bapak Sri Haryono. The question is, what more reservoir clastic stone with carbonate stone and which one long age to produce? Maybe Pak Sri Haryono, could you please elaborate your question? Because I assume that it's not a complete sentences, maybe.
If I can understand it, it's a very very wide question, like between plastic and carbonate, which one is to produce for long? It's very difficult question to answer, to be honest. Means it's not about whether it's plastic or carbonate. It depends on many other things. Means the reserve, the permeability, the connectivity. We have a great plastic reservoir in the world. We have excellent carbonate reservoir of the world. They both are prolific producers, depending on what is the what are the quality of the reservoir. So it's not an easy question to answer if you just which one is a better reservoir, like plastic or carbonate. We have both reservoir which are producing excellent in the world. So yeah, so that reservoir needs to be studied and the properties need to be measured. And regardless whether it's carbonate or plastic, if it is a good reservoir with good potential, it will certainly produce.
All right. We move on to the last two questions, sir. The next question is from Pak Julian Tapanjaitan. If only there are two options available provided and we have to choose whether image plus NMR and image plus 3D multi-component resistivity, Which one is your recommendation for low resistivity and thin bed environment?
This is a very, very good question. I absolutely like this question. And actually, we had a paper on this, and this is a question from the side of VOI, what we call a value of information analysis. Like when you have a limited budget and you have to select one out of other, and we all go through this process pretty much every day. Our wish is always to run everything, but definitely we cannot have that luxury. So yes, personally speaking, if it is a thin bed laminated sand shell, then image plus 3D resistivity can go a little bit higher in the selection criteria. uh, and if it has a lot of silt kind of material, because in those kind of reservoirs you have both laminated sand shell section and the silt section. So in that kind of silty section where you have an expectation of a lot of bound water, probably the NMR can be of a better choice. I know this is a very generic answer, and the VOI analysis actually needs to be done before giving you this answer. But in a very generic sense, I say if it is a pure laminated sand and clay type of reservoir, and the resistivity low is mainly because of the presence of a lamination, then probably image and 3D is a better combination. Whereas if you have a decent amount of silt in the reservoir, and the low resistivity is mainly because of the bound water rather than laminated shale, then image plus NMR can be a better option. But yeah, given a choice and money, I should go for all three.
Okay, thank you, Pak Saikat.
You are welcome. I really appreciate this question, because we know we wish to run all, but every time we have to compromise. And yeah, this VOI analysis is very important in that. What our objectives are, and which tool is more suitable to get me that answer.
All right, we move on to the last question of our session today, Mr. Saikat, from Bapak Yulianto again. Speaking about Tritex tools, if I am not mistaken, we can use directly the RV to calculate the SW in the thinly laminated interval, aren't I? And the second is one of the role of imagery logs is for sand counting. The question is, could we do it if we have only NMR logs?
Okay, so first question, yeah, there is a problem. You can using RV to calculate SW in a, let's say you just take a saturation equation and use RV to get an SW. That is a possibility, but the thing is that if you do it, it's not 100% accurate. The reason being, the RV is still not the resistivity of the sand. It's somewhere in the middle. RH is definitely the lower one, RV in the middle, and resistivity of the sand is actually even more. If I can go back to the slide, yeah, probably here. So if you see the resistivity of the sand, if we have 10 ohm meter and resistivity of shale is 1.8 ohm meter, RV will be always somewhere in the middle. So if you use directly this RV, certainly you will get a better hydrocarbon saturation than your standard log, but still it is not the accurate representation. So there is a way to calculate resistivity of the sand and use that resistivity of the sand instead. That is the best way to do it. That means you are using the proper resistivity of the sand, and you will get even a better hydrocarbon saturation. So that's the question number one. One of the role of image log is for sand counting. Yes, certainly image log does a lot of other things, and sand counting is one of them. Could we do it if we have only NMR logs? So NMR will not give you a sand count, but it certainly give you an idea of the movable fluid, which is related to the reservoir quality. So that can be an indication of good quality reservoir. The greater the amount of movable fluid, higher or the better the quality of the reservoir. But it doesn't exactly give the sand count. That is something which we can get it from image log. We can get some idea from the 3DEX as well, but image log is the highest resolution log that you can expect in logging industry, and the sand count from there is generally as a quite useful.
All right, thank you, Mr. Saikatas. Maybe from Mr. Yulianto, do you have any follow questions?
Thank you very much for the explanation.
All right, you're welcome, Mr. Yulianto. So, Mr.
Yeah.
Saikatas, do you have anything to say?
No, no. From my side, it's an absolute pleasure. No doubt about it. It was a very interesting discussion. Absolutely fascinating questions, and I am really happy that I managed to connect with you all. And thank you for giving me this opportunity. I really thank you from my bottom of my heart.
All right, Mr. Saikat, maybe the last question for me. The back to the basic and the simple questions related to the Indonesian production target, 1 million BOPD and 12 DSFPD in 2030. As the formation exploration discipline lead for many years, you absolutely have studied about many characteristics of formation exploration in many places, maybe including Indonesia. The question is, what do you think about the challenge and opportunity of deep water exploration in Indonesia for several years ahead?
So definitely, okay, very excellent question, no doubt, and certainly the deep water challenges is they are very common. You know, this deep water setting, whether it is Indonesia or anywhere else, the challenges are quite generic when it comes to formation evaluation. So certainly, my advice or my thought or my take on this is just first to understand the issues and the challenges. That is the stepping stone. I have said it probably many a times. Deep water is a challenging environment. It's it is a very promising area. Obviously, Indonesia being a very mature oil and gas producing country, it has got a huge experience and legacy when it comes to oil and gas. That is excellent. But now the problem is most of the easy targets are already being explored and being produced. So that's the challenge. So you do have a plethora of knowledge in Indonesia because of this really long production history. So we need to capture that knowledge and channelize it to the deep water. But we need to have an open mind because deep water will be more challenging. We may not be able to get a lot of information from conventional logs that we are generally used to. So we need to accommodate advanced logs, advanced solutions, which are available. That's one good thing about it. It's not like that it's not available, but we should keep our mind open to embrace those solutions and use it in deep water exploration. We need, as I told, we have to have a advanced log like image log, 3D resistivity type of log, NMR log, mineralogy log. Not everywhere, obviously. I'm not saying you need it everywhere, but when it is needed, that is important to deploy. And I think the conclusion side, I can just put it again. There are one or two places which is very pertinent to your question, and then this key well concept. You know, this is also quite important when it comes to deep water exploration. We may not get the luxury to run every tool in every well, just to be practical. But when we plan for it, having the concept of key wells, identify few wells in those areas where we should be able to acquire all the data and gather all the knowledge. And then later on, in the infill wells, we may not be able to probably deploy everything. So the planning is very, very important, what I believe, and keeping an open mind to embrace newer technology, that is definitely key. And the dialogue, that's what we are having now, the sharing of knowledge, because people have already done a lot of work in deep water, and the materials are available, papers are available, the knowledge is there, so that connection needs to be made. And if we can do that, I'm certain that we can certainly have a very successful and fruitful deep water exploration and development campaign.
All right. So the key is well planning and open mind to new technology, right?
That's the take.
All right. Thank you to Mr. Saikatdas, and I would like to represent the committees of ISPG Research Forum 2021 to say thank you very much to Mr. Saikatdas and Becky Hughes for providing us a very fruitful and comprehensive discussion about formation evaluation in deep water. We strongly hope that our discussion today could be very useful for us to support Indonesian geoscience and production target. There's 1 billion BOPD and 12 the SCFPD in 2030. And ladies and gentlemen, we have reached the conclusion of our seminar today. For all participants who would like to, please open up your camera to reach the photo session. We would have the virtual photo session together. Please, to all of the participants, kindly open up your camera. All right, we'll wait for about maybe, sir, Mr. Saikatas, could you please stop share your presentation?
Oh, okay, I'll stop sharing.
All right.
Okay.
All right. We will wait for about 5 seconds to make sure everyone is ready with the camera on. All right. Thank you to all participants for the enthusiasm to have this technical session, this technical discussion in this Saturday afternoon. Really interesting. All right, I think everyone is ready, and the committee will start capturing in 3, 2, 1. Once again, don't hesitate to give your biggest smile because the committee will start in 3, 2, 1. All right, thank you to all the participants, and please don't go anywhere. Please don't go anywhere before I end this seminar because I would like to inform you the following matters. Wait a minute. So, ladies and gentlemen, we would like to inform you that after this event, we will still have next post-event workshop. That is about oil and gas in ARGIS business process that will be held in April 21st to 22nd. So make sure that you still follow us at Instagram at
I think I lost him. I could not hear anymore.
Mas Adit, no sound.
Yeah, even I can't hear.
All right. Can you everyone hear my voice?
Yes.
Now we can hear you.
Yes, I think there's a little bit trouble with my earphone. So, ladies and gentlemen, thank you to all of the participants who have joined us today. We look forward to see you again at the next ISPG Research Forum event. And may you have a very good day and stay safe. Good afternoon and goodbye.
Thank you. Thanks a lot.
Thanks a lot, sir.
Bye-bye. Take care.
Take care.
Thank you, Pak Saikadas. Pak Susilo Baskoro, thank you.
Yeah, thank you, Pak
Negatif.
Julianta, and thank
Yeah.
you, Pak Susilo. for
Okay, thank you.
helping us.
Thank you. Welcome.